In this skill, we're going to be using the Henderson-Hasselbalch equation to figure out the pH of a buffer that was made by an acid-base reaction. In this question, we have a scientist who mixes 1.64 moles of perchloric acid, HClO4 solution, with 2.23 moles of ammonia, NH3 solution, at 25 degrees C. We're told the total volume of the solution is 1.29 litres. So we can see here our molecular and ionic equations. HClO4 is a strong acid, meaning that it completely dissociates in water. NH3 is a weak base, meaning it only partially dissociates in water. And NH4ClO4, that is our salt that we produce. You can see that the ClO4 doesn't appear in our net ionic equation because that ion is the same before and after, because the strong acid is fully dissociated. Our goal is to figure out how much of our weak base and its conjugate acid we have remaining after this reaction happens, because that's what's going to form our buffer solution. So we start with 1.64 moles of HClO4, and we have 2.23 moles of ammonia. We can see from our equation that we have 1 mole of HClO4 reacting with 1 mole of ammonia. It's a 1-to-1 ratio. So based on that, we can see that NH3 ammonia is in excess. So that means we're going to have 1.64 moles of HClO4 reacting with 1.64 moles of ammonia to form 1.64 moles of NH4ClO4. So we're going to get 1.64 moles of NH4ClO4 produced, and we're going to have 2.23 minus 1.64, which is 0.59 moles of ammonia remaining. And since there's one ammonium ion in a formula unit of NH4ClO4, that means of ammonia ions is also going to be 1.64 moles. So we've got 0.59 moles of NH3 and 1.64 moles of NH4 plus remaining after the reaction. Next, we need to figure out our concentrations of those. We were told the total volume of the solution is 1.29 litres, and we know the number of moles. Here's our molarity equation on the solutions page of the reference sheet. Molarity equals number of moles divided by volume. Molarity equals number of moles divided by volume. So to find the molarity, we're going to do the number of moles, so that's 0.59 for NH3, divided by the volume, which is 1.29 litres. That gets us 0.457 molar for our concentration of NH3. Then for ammonium, we've got 1.64 moles divided by the volume of 1.29 litres, giving us a molarity of 1.27 molar. So we can fill that in here as well. Okay, so we've got our concentrations of our base and our conjugate acid after the reaction. Here's our dissociation equation for our base, NH3. It reacts with H2O to form NH4 plus and OH minus. So this is our base. This is our conjugate acid. And we're given Kb is 1.8 times 10 to the power of negative 5. To figure out the pH of this solution, we're going to start by figuring out the pOH, since we're talking about a base, using the Henderson-Hasselbalch equation. So let's head to the reference sheet. Here on the acids and bases page of the reference sheet is our Henderson-Hasselbalch equation. Here's the equation for pOH for a base. pOH equals pKb plus log of the concentration of our conjugate acid divided by the concentration of our base. So in this question, NH3 is our base. So that's going to be on the bottom of our fraction. And our conjugate acid is NH4 plus. That's going to be on the top of our fraction. So that's going to be our Henderson-Hasselbalch equation for ammonia, NH3. So we can go ahead and fill that in here. So we've got NH4 plus on the top and we've got NH3 on the bottom. So to figure out the pOH, first we're going to need to calculate pKb. Now remember, P means negative log. So pKb means negative log of Kb. So all we have to do is put our number for Kb, which we were given as 1.8 times 10 to the power of negative 5, and do negative log of that. That's going to get us a pKb of 4.74. So all we need to do now to find pOH is substitute the pKb and our concentrations of our base and conjugate acid into our Henderson-Hasselbalch equation. So we've got pOH. Our pKb we just calculated is 4.74 plus log of the concentration of ammonium, which we figured out was 1.27 after the reaction's finished, divided by the concentration of ammonia, which is 0.457. If we put that into our calculator, that gets us a pOH of 5.19. So we can go ahead and fill that in over here. Our final step now is to find our pH. We already know our pOH, so we can use our expression here that converts between pH and pOH at a temperature of 25 degrees C. We've got pH plus pOH equals 14 at 25 degrees C. Since we're trying to find pH, I'm going to subtract pOH from both sides, so that will cancel out on the left, leaving us with pH is equal to 14 minus pOH. So we can go ahead and put on our numbers. pH is equal to 14 minus the pOH we just calculated, which was 5.19. That gets us a pH of 8.81. So we can go ahead and fill that in here. So to summarize what we've done here, the first part of the question was like our acid-base reactions questions, where we're just using the given moles of the acid and the base to figure out which thing is in excess, and we're using that to figure out how many moles of our either base and conjugate acid, or it might be acid and conjugate base, we have remaining after the reaction. Then we're going to write a Henderson-Hasselbalch expression for the pH or pOH of the solution, and we're going to use the concentrations that we calculated along with the Ka or Kb given in that equation to figure out the pH or pOH of our solution. We can also just do a check to make sure that our answer makes sense. In this question, we had a concentration of 1.27 for our NH4+, which is greater than a concentration of 0.457 for our NH3. So we had the top of our fraction being bigger and the bottom being smaller. As a result, that means that the fraction is going to be greater than 1 overall. And log of a number that's greater than 1 is going to be positive. So this whole thing is going to be positive. So that means our pOH will be our pKb plus a positive number. So our pOH should be greater than our pKb. And that's what we found here. We found our pOH was 5.19, which is greater than our pKb, which is 4.74. So that matches up based on the conceptual questions we've already done.